Hi, I'm here with a friend, Dr. Robert Jameson, who's Professor Emeritus of Mathematics at Clemson University. So we're privileged to have the professor here. And he's also an affiliate of University of Haifa in Israel, just part of his verite. And he's a very prolific published journal writer. And his works are heavily cited throughout. That's true, isn't it?
Yeah. I'm pleased with the number of times.
Good. I don't know how to compare it, but it seemed to me that you were cited often.
Thank you.
So, what Dr. Jameson is going to talk about is the history of the concept of infinity, which is way outside my wheelhouse, which is just ordinary philosophy. My specialty is perception. But I'm eager to hear, because I wanted to say that Dr. Jameson pointed out to me when he was suggested this idea, that infinity is an old, evolving concept which has implications both in mathematics and in philosophy and in theology. So it's very interesting subject, and let's turn it over to Dr. Jameson.
Okay, thank you very much, Chris. Just before coming out here on the step, Chris said, well, I hope you have a lot to say. And I said, well, I gave 3 one-hour talks on this subject in my Sunday school class, and there was still a lot of material that I didn't get to. So there is a lot to say about infinity and the history of infinity. And my friend who brought me here, Eric, I said, well, there's this story with the hashish. And he said, well, you better open with that because that will catch people's attention.
Okay.
So, and Chris just mentioned before we came out here that he was familiar with Georg Cantor, who was the founder of set theory, and that Cantor was also the person who developed the modern theory of infinity in mathematics.
And set theory.
And set theory, right? It's connected.
Which I actually at one time asked you to explain to me, set theory, and I tried to listen to videos about it, but it just flew over my head.
Well, I'll see
but
what
I got
I
that
can
much.
do.
Okay, thank you.
So the story is this. I was an undergraduate at Clemson University. I went back there as a professor many years later. And I had been in a summer program with a group of very bright guys. I was privileged to be among them. There were 12 of us in the program. And 4 of us decided we weren't going to live in the dormitory. We were going to get our own apartment. Here we were juniors in college. And so that was a little bit of a wild experience, and we became very good friends. And one of them, Andrew Samizi, lived in New York, and he invited us to come to New York for Christmas that year. And indeed, we went to New York. And Andrew had an older brother who was in Yale as a graduate student. So he said, well, let's go on up to Yale and visit my brother. So I'm a fairly old guy, so this is 1968. Okay, this is 1968. So when I went into Clemson in 66, everything was normal. In 67, 68, everything had changed. People were smoking marijuana, they were doing drugs, they were hippies, all that kind of thing. So when I was there, the brother passed me this math book on set theory by Felix Hausdorff. Okay. And I started reading this book. And Hausdorff is explaining Cantor's theory of infinite sets, of cardinal numbers and ordinal numbers. So let me just explain the difference between those. So cardinals numbers are there's 1, 2, 3, 4, 5, 6 chairs that I'm looking at here. Ordinal numbers are I'm looking at the first chair is a couch, the second chair is an armchair, the next chair is just kind of a Quaker-style chair. So the fourth chair is this other guy, so I'm counting first, second, third, fourth when I'm putting things in an order. That's an ordinal number. And if I'm just counting the number of things, that is a cardinal number. So in our ordinary life, we don't really think about there being much difference between those two. But when we get to the infinite, there's a major difference between them. So anyway, I was reading this book by Hausdorff, and Hausdorff is explaining all of this stuff. And I was a junior in college, but remember, I was a pretty bright guy because I was in the summer program with these other bright guys, all of whom were brighter than me, but nonetheless, I was with a group of very bright guys. And this was just blowing my mind, all this theory of infinity. And then as the evening wore on, somebody offered me some hashish to smoke. Now, of course I had tried marijuana, but I wasn't a cigarette smoker, so I didn't know how to inhale, so the marijuana didn't do anything to me. But I smoked this hashish, and I fell asleep. And the next morning when I woke up, I thought, you know, when I smoked the hashish, I became silly and fell asleep. But when I read the Hausdorff, it just completely blew my mind. That's the high I want. I don't give a damn about these drugs. This theory of infinity is just incredible. And it carried on. It wasn't just like it stopped that time at Yale. I became fascinated and obsessed by it, and it played a major role in my dissertation. Okay. And I'll digress a moment to say this. When I was teaching, I liked to digress a lot.
I read that online to see your reviews by students. They often commented
Did you read
about
students?
I did. I was trying to do my homework.
I didn't know any of those were online. I'm going to have to go in on YouTube and say, I want this taken down.
You should. Like, a lot of them. I saw, this is what I said, like Dr. Jameson doesn't always teach us math. He goes off onto these tangents. And I thought, well, I would have liked a teacher like that. They were probably spiritual, philosophical.
Well,
no?
They were often tangents on the history of mathematics.
Okay,
I didn't get into politics.
Okay, but I love tangents. So
I didn't go into it explicitly, although I did very much like Rudolf Steiner's Waldorf schools.
Okay, I want to mention one thing, but maybe the audience doesn't know, is that Dr. Jameson's specialty is theoretical mathematics.
Correct.
It's not just arithmetic and stuff like that, or calculus and stuff.
That's correct. So when people say, oh, did you teach calculus? Yeah, of course I taught calculus, but that's just the beginning of all this stuff. That's not the end of it. So calculus was invented by Newton, 400 years ago.
And Leibniz.
And it's been, and Leibniz, yes, okay, yes, Leibniz. And we'll come back to Newton and Leibniz later on. So I've digressed. So where was I in the digression? Oh, you brought up the students and my evaluation.
Oh, I'm sorry. That was a digression itself.
That's right. But on the topic of digressions, typically if you have a voluntary response survey, the only people who are going to respond are the ones who have something negative to say.
I didn't know that. Okay.
Oh, yeah.
I had another professor friend who would read me these terrible reviews, so I didn't know that.
The ones who are happy, they don't bother to say anything, but the ones who are angry, they want to get their venom out there. So you're more than likely, if you're reading reviews of some professor, that most of them are more than likely going to be negative.
Thank you for telling me.
And so, but what I did find out, so you read.
You are a professor emeritus, so you survived. You not only got tenure, but you made it through.
I made it through. It wasn't just a matter. Anyway, that's an digression I don't want to go down.
Okay, well, let's get back to the theory.
So first, we're going to finish the digression of the digression, and that is on the student evaluation. So I found out that roughly half of the students didn't like it, and half of the students, like you, liked it.
Yeah.
And so I would start the class by saying, I have a tendency to digress a lot, and half of you don't like it, and half of you do. And I like it, so I'm probably going to continue making digressions. So that's the way it's going to be. And we'll probably have quite a few digressions. We already have had enough digressions. So where were we in the serious thing? Oh, yeah, my dissertation having some connection with infinity, and my early work in mathematics.
And Cantor.
Mm-hmm.
And you were explaining, Cantor, about the two types, ordinals and the other kind of numbers.
Cardinals and ordinals. Mm-hmm. So, but I don't want to go into those right now.
Okay.
I want to talk about me before I talk about Cantor.
Right.
So, in my careers, so the early stages of my career, having encountered these notions of infinity, they were very important in a certain kind of mathematics called functional analysis, and my early work was closely connected to functional analysis. When I had my first daughter, I thought I would like my daughter to be able to understand something about what my mathematics is. So I stopped working in the infinite realm, and I started working on things that were finite: geometry, geometric figures, networks, and stuff like that you could draw pictures of. And I was just thinking about it again in terms of this conversation. So I stayed within the finite realm for years until the very end of my career, and the last paper that I wrote involved something called Zermelo's axiom of choice, which comes from the theory of infinite, and I won't talk about it now, but I will talk about it later. So, I was telling to my friend Eric, who brought me down here, and I also said it in the Sunday school talks, there are basically four main points, main issues, main things to focus on in discussing infinity. First of all, there's the infinitely large. Or you could say the infinitely long, which is the same sort
about
of
time.
About time. There's the infinitely large, there's the infinitely small, there's the potentially infinite, and the actual infinite. Okay, so now we're going to start the history. And furthermore, I'm talking about the history of infinity as far as Western mathematics is concerned. I'm not talking about it in terms of mathematics in India. I know nothing
Vedanta, stuff like that, right?
Right, I don't know. I know very little about that. But the Western mathematical tradition, starting with the Greeks. So, as possibly some people know, the Greeks did not have the concept of zero.
The Arabs came up with it.
No, it originated in India.
Oh,
and so the Arabs in their contact with India, they picked it up from India, and then it was transferred from North Africa, the Arabs in North Africa, to a fellow called Leonardo of Pisa, also known as Fibonacci, who brought the Arab number system into Europe in about the 1200s. So no, the Greeks did not, in spite of the fact that for 1,000 years of mathematical tradition, and they did extremely deep mathematics, the Greeks never came up with the idea of zero. And they were also very suspicious of the idea of infinity. They were suspicious of the idea of an actual infinity. They were okay with the idea of a potential infinity. So let me give you an example from Euclid. I hope hopefully will be known to some of your viewers as the one who wrote the 13-volume set on the elements, containing a lot of geometry that's taught in high schools now and beyond. So one of the theorems in his Elements is a theorem about prime numbers, so numbers that have no divisors other than themselves and whole numbers in this property. And what we would say today is that there are infinitely many primes. So we accept today, because of this contour that you mentioned before, because...
I just want to say I only know about him because I looked it up last night.
That's okay. You still know about it.
I learned.
You learned. So, in giving these talks in church, I knew a lot when I started. I knew a lot more when I finished, of course, right? Because I was looking things up. So I knew I knew the questions to ask and where to start, but I found out a lot more. Okay, so go back to Euclid 300 BC. His elements, his theorem about the primes. And today we would say there are infinitely many primes, and our proof of this fact today is essentially Euclid's proof. But Euclid didn't say that because he didn't have the concept of an actual infinity. What Euclid said was, if you give me any list of primes, it has to be finite, of course, because the Greeks didn't believe in an actual infinity. So if you give me a list of primes, 110 million, however many primes you want to give me, I'll find a prime that's not in your list. So that's how we're potentially infinite. You have something that's finite, but you can always add something to it. You never actually get to infinity, but the process never stops. Or the process doesn't have to stop. You can keep on going. So, okay, that's in terms of the infinitely large. And then I'll say something about the infinitely small in this context as well, the Zeno paradoxes. Okay, there's the camera over there that I'm looking at right now. Suppose I want to walk over to that camera. According to Zeno, what I have to do, I have to get out of the chair, of course, first, and then I have to walk halfway to the camera. And then before I can reach the camera, I have to walk halfway of what's left. And I'm still not there, so I have to walk halfway of what's left after that. And I have to walk halfway over and over and over again. So how can I possibly reach the camera because I have to walk all these halfway? Zeno's paradox. And it has to do with the infinitely small, because these amounts of half steps that I'm taking are getting smaller and smaller and smaller. Okay, so we have this paradox with the infinitely small in terms of Zeno's paradox. We have the problem with the Greeks not accepting the actual infinity, but being okay with the potential infinity. So I want to say something else about the Greeks before moving on, and that's Archimedes, who is considered to be one of the greatest mathematicians of all time. So he lived, Euclid was about 300. We don't really know much about him, so that's very approximate. Archimedes we know more about. His dates are around 280 BC or something like that. So a little bit later than Euclid. And Archimedes wrote this amazing book. If you wrote anything in those days, it wasn't a letter, it was a book, right? So it's a very short book. And it's called The Sand Reckoner. And Archimedes starts out by saying, there are some people who say that there are an infinite number of grains of sand on the beach. And he said, that's not true. I'm going to show you that I'm going to count the number of grains of sand it would take to fill up the entire solar system. So that's the sand record. And he says, and I'll say before he says it, I'll tell you what. So we talked a little bit about the Hindu Arabic numerals reaching the west through Fibonacci, and how we now can write 100, 1,000, 100 million. We can get up to the national debt, 1 trillion, 17 trillion. You just keep adding zeros. Well, the Greeks didn't have that number system. So they didn't have names for these huge numbers. They had names for 1,000 and so on like that, but they couldn't go up to 100 million. Okay, so that was a problem for them. They didn't have a way of naming these large numbers, and they didn't have a way of representing them. Because alpha, the first letter of the alphabet, was also 1. Beta, the second letter of the alphabet, was 2. And so on. That's also true in Hebrew. So the letters of the alphabet served as their numerals, but how can you put them together to get arbitrarily big numbers out of them? But without the concept of zero. See, the point of zero is that even though it's nothing, you keep adding it, it can make things bigger and bigger. Okay? So what Archimedes said I'm going to have to do is I'm going to get these big numbers, and I'm going to have to invent names for them as we go along, which is exactly what he did at the Sand Reckoner. So he'd get a huge number, and he'd say, well, I'm going to call this Quiddly-Potch, and then I'm going to do all this other stuff, and I'm going to take all these Quiddly-Potches of Quiddly-Potches, and I'm going to call that a Dama-Dam, or whatever. I should have read my Archimedes before coming here so that I know the names he gave it to. So in this way, he calculated the number of grains of sand it would take to fill up the solar system. And he says, this is a heck of a lot of grains of sand, but it's not infinite. So that was an amazing accomplishment as far as I can see. And here's a digression. Let's see, when did this happen? I know it happened in the late 1990s that a manuscript called a palimpsest became available and was on sale by one of the auction houses, Sotheby's or somebody like that. And this palimpsest, so what is a palimpsest? Well, you take a manuscript, and this is like from 900 AD or something. And so in those days, writing a manuscript was very expensive because you had to have the cow's hide and everything processed right. And so you have this palimpsest, you had this manuscript that was there, an ancient one. And then the monks said, oh, that's just a bunch of ancient stuff. We don't need that. We need to put liturgical stuff. So they turn it 90 degrees, and then they write on it at 90 degrees. So the underlying writing wouldn't be a real obstacle to reading the new writing. Okay. Well, one of these palimpsests became available in one of these auction houses. And its importance was it was discovered that the writing underneath was something from the sand reckoner. Now, it wasn't Archimedes' copy, of course. That's long gone. Maybe it was written 500 years after Archimedes, maybe 1,000 years after Archimedes. But it was, and I'm looking over this way because there's a lady doing the video, and so I'm talking to her as well, okay? As well as my favorite audience out there. Okay. So this went on sale. I found out about it, and I bid on it, of course. Of course, I'm joking.
Oh. I brought it with me today.
Of course, I'm joking. But what I could buy was the catalog. So you have these expensive items going on sale. They produce a catalog which describes the object. They get pictures of it and so on like that. So I was able to buy the catalog for this palimpsest. And that was a prized possession. I've moved a number of times since then. I'm afraid I don't know what happened to that catalog. And nobody knows exactly who bought it, but there was some conjecture it might have been Bill Gates, somebody like that. I mean, this item would have cost $1 million, $2 million, who knows exactly how many. So, very valuable ancient artifact from the sand reckoner. That was one of my particular reasons for being interested. Oh, the manuscript of the sand reckoner is out there. So, there we go. I think I've covered everything I want to call about ancient Greece, unless you have some questions.
No, that was all very clear.
Oh, I'm sorry. I was hoping.
No, I thought I'm learning a lot. I mean, that's really. I studied the Greek philosophers, but we didn't talk about their mathematics. I knew about Euclid, but that's about it. And
well, how could you study the Greek philosophers without talking about their mathematics? I don't know how that's.
Well, there's a lot of metaphysical theories that they had.
Well, okay, I have to make another digression.
Okay.
Okay, there was.
I know about Zeno, for instance.
You know about Zeno?
Yes,
yeah, that's a big philosophical.
That's right. They teach you that.
That's a big philosophical.
So maybe they taught me more mathematics than I thought about. Aristotle, of course, is logic, syllogisms. That's very connected to mathematics.
Foundations of mathematics.
Right.
That's right.
That's right. Okay.
Um,
I know later, Bertrand Russell and
well, we'll get back to him.
Okay,
we'll
good.
come back to him. He's
Good.
after Cantor, so we'll come back to him after
Okay.
we move forward another 1,000
Right.
years or so. So, why you should have encountered this? Okay, you know about the Pythagoreans.
Yeah.
Okay.
Mhm.
And do you know their philosophy that everything is number?
I do, and
Okay.
I've quoted that. Yeah.
Okay. So, what the Pythagoreans discovered, and you're probably familiar with this too, was that
Harmonies that
the
have
harmonies
okay.
and the how if you cut the length of a string in half, it goes up by exactly half.
I didn't think of that as mathematics, but now that you mention it, of course it is.
Of course, it's mathematics.
It kind of seemed musical.
Oh,
Like that.
yeah, you'll have to, yeah.
Oh, and Cantor, I want to just brag that I learned that he was a violinist.
Oh, now that's something
But we'll get to that. You haven't even gotten
I
to
may have
Cantor.
read, but I don't remember. So congratulations
Oh, good.
to you. Okay. So actually, many mathematicians, that would be another digression I may get to later on.
Like Einstein,
But,
yeah.
like Einstein, yes. So you're reminding me of too many anecdotes. That
Sorry.
too far afield.
I-
So the Pythagoreans said everything is number. So
Right.
the musical scale was all based on these ratios.
I want to say, just several people said that everything is number, including Newton.
Oh, but that's much later.
Yes, I know, but I'm saying throughout history, and it's in the Jewish Bible too.
Well, we'll come to Chronicler, who was one of the main enemies of Cantor, who basically said that. So we'll come back
Good.
to that. So, what was discovered, however, and some people say it was the Pythagorean, some people say it was a little bit later. So, the everything is number is based on what they call commensurates. So, the idea of a commensurate is that if I have let's say a painting, and it has a certain height, a certain width, then I can find some unit, maybe very small unit, that I can exactly measure off the length of the height, and also with that unit measure off the length of the width of the painting. So that's a commensurate. So that's very important in the Pythagorean theory, that you can, given any two lengths, you can find a measuring stick that is such that you can use that measuring stick to get a whole number of things to describe the length of one of the segments, and also a whole number for the other. The disastrous discovery, which led to what was called the first crisis of mathematics, was the discovery that if you take a square, the side length of the square and the diagonal of the square there are no commensurates. They are incommensurate with each other. So this blew the Pythagorean idea that everything that could be measured in terms of whole numbers in some way, they blew it out of the water. So that was the first. So what happened with this? So today we say that the square root, so the length of the diagonal of the square is the square root of 2 using the Pythagorean theory. I won't go into all of that, but some of your listeners may be familiar with that already. So the length of the the diagonal of the square has a ratio of the square root of 2 to the length of the side. And in modern mathematics, we say that that's an irrational quantity because it cannot be expressed as a ratio of two whole numbers. And I think it's in Timaeus. Isn't there a discourse, dialogue by Plato called Timaeus? I think, and it's a relatively short one, I think. And I may be getting the wrong book, but I think it's in that one. There is one of the dialogues in Plato where it's shown that not only is the square root of 2 incommensurate, but so is the square root of 3 is irrational, and the square root of 5 is irrational. It may even go up to 7. What they did not prove is anything like the square root of any prime number is irrational, which is true. But so is more. So okay, there's a philosophy book that contains this very fundamental mathematics. So Plato and his school were very much aware of this. This was important to their philosophy, this idea that no, you can't measure everything. You can't find a unit of measurement that's small enough to measure everything. So maybe that's getting back to the idea of the infinitely small. So, wow, I'm exhausted. I need to take a drink.
Take a drink.
This is water. Did I ever finish? I did finish the hashish story. Yes. Okay. So this.
You're doing good.
This isn't gin or anything like that.
By the way, since you're having a sip of water,
It's not water. It's called Splash. It's Mildberry.
Oh, well, nice.
Oh dear.
You got it out of the fridge over there or something?
No, Eric gave it.
Okay. Well, anyway, I'm thinking, it's true that I never thought about it, that so many philosophers were mathematicians also. Leibniz was a philosopher.
Oh, absolutely. Leibniz.
I'm sorry. I only read it. I think people don't talk about it. And Bertrand Russell, and now you're mentioning Plato. I think of Plato was geometry, and I didn't realize it was mathematics too, like that.
Well, the square root of 2 shows up as a diagonal of the square.
Right.
So it comes.
So it's related to geometry.
And
I know that Pythagoras was the influence on Plato.
Oh yeah, he's an influence. Each one successive generation was an influence on the next.
Yeah.
So we better stick to the infinite, or else this will be an infinitely long talk. So at this stage, I think we finished with the Greeks. We may have to go back to them at some point, but we basically finished with the notion of infinity, something about their mathematics, the role this played, how it showed up in their mathematics. We saw Archimedes as being kind of the culmination of this process. And I will skip briefly over the Middle Ages, except to say the Greeks kind of said, okay, there is an infinite, that's the infinitely good or something like that. And St. Thomas Aquinas said, okay, this, in the physical world is only the potentially infinite, but God is the actual infinite. Okay, so we have that. Now, we come forward to Newton and Leibniz, but we're in an English-speaking country, so Newton is the founder of the calculus. If we were German, Leibniz would be the founder.
Fine. But they told us about their fighting over the credit.
Of course, yes. I think Newton was the more aggressive one. So in developing the calculus, what Newton had to do was he would analyze these, say, motions over a period of time, and to study them, he would divide the period of time into smaller and smaller units. And finally, he divided into where it was infinitely small, and then he would have some way of performing these arithmetic computations with this infinitely small. And he came up with the theory of gravitation, and he was able to derive Kepler's laws from his universal law of gravitation using the calculus. So one of Kepler's laws, for example, is that the planets move in an elliptical orbit around the sun. And then Newton kind of retired from that, and he was very much involved in theology.
And the Bible code.
The Bible code, I don't know anything.
The numbers of the Bible code.
Theology, I don't.
What would they call that? Oh well, but maybe I heard a bullshit, Discovery Channel nonsense.
Yeah. Who knows? I mean, I've seen some of that kind of stuff, and it seems kind of. There are going back and looking at picking out every seventh letter of each line of the Bible.
Yeah, that's what I'm talking about. That's not real?
No, that's not real.
Good.
And one can, it's not just, oh, I don't believe that, I don't like it, but there are solid statistical grounds for why that stuff it can happen, but it's not statistically valid.
Correct. It's nonsense.
It's basically nonsense. So that if you want to predict the future, you have to choose the right Hebrew version of the Bible anyway to start choosing which lines, and so on to look for. So no, that's definitely not the way to predict the future. Newton gave a better way of predicting the future. He predicted that the sun is going to rise tomorrow because the planets are kept in their course.
And explained why it's going to rise.
And explained why, exactly why. And you could do even more calculations about that, about how much shorter the daylight is from day to day now that we're in the winter.
Over the year, yeah.
Over the year. So, but one of the things I knew early on was I knew Newton had been involved in theology towards the end of his career rather than doing mathematics. What I learned later in preparing these talks for church was that he was an anti-Trinitarian. He did not believe in the Trinity, and therefore he did not publish most of his theological writings in his lifetime because it would have gotten him in big trouble with the church. So they appeared in letters, but they weren't published while he was alive. So Newton addressed the problem of the infinitely small in developing his calculus. And in Leibniz, Newton used these things called fluxions in this notation, which I assumed had basically died out. But a friend of mine in physics told me that the derivative of a motion with respect to time is still denoted by putting a dot over the variable. That's not the way it's taught in calculus in college, but apparently the physicists still use it. But Leibniz was the one who came up with dx dt as the notation. So dx represents an infinitely small change in the variable x divided by an infinitely small change in the variable t, time. And this is the ratio of these two infinitely small things. And then comes this Irish bishop a century or so later. He says, what the hell does that all mean? This doesn't make it. How can you take one infinitely small thing and divide it by another? And in Newton, he says, okay, Newton is working with these infinitely small things, and he does all this arithmetic, and then suddenly he just says, well, they're negligible, and throws them away. How can you do that? They're ghosts of departed quantities, he called it. So Bishop Berkeley, this bishop, he didn't dispute the results that Newton got. What he disputed was how he got them. There was no adequate logical foundation for the mathematical manipulations that Newton was making.
Are you talking about Berkeley, that Berkeley was named after?
I don't know if that's true or not.
George Berkeley?
I don't know that.
Yeah, he was.
An Irish bishop?
Yeah, so I thought you knew, so I was just...
I didn't know that.
Oh, yeah.
Well, you know a lot of things.
Well, I did my day treatment on Berkeley, so that's why I know.
Hey, I'll have to look that up. I'm not sure if I trust you.
Go ahead. It's everywhere. It's common. You look up Berkeley, California, and they'll say named by... It was named for a poem that he recited, a line he wrote. Westward, there's the Road of Empire. And so when they were naming the city of Berkeley, they named it after the Irish bishop.
Oh, then it must be from the 1800s, right? Into the 1800s.
Well, he wrote he lived in the 1700s.
1700s.
Yeah. Yeah. It's real trivial. I mean, but I always tell people to try to get them interested because everybody likes Berkeley. The city. The town. So they're all amazed. Oh, really? It was named for a philosopher? I didn't know that.
Well, a philosopher who questioned the logical underpinnings of Newton's work.
No, I didn't know that. That's amazing.
We're learning from each other.
Yes.
So that's the way it should be. But I'm the one who's supposed to
I
be...
just want to tell you something about Berkeley. Because he was always my favorite philosopher. Because they said he was such a nice guy. And I said, Newton, by the way, they said was a nasty guy.
Yes.
Okay. Right. So I always said, well, I like Berkeley because I like his, his ideas, but also he was a nice guy. But then they just learned that when he was staying in America before the United States was formed, he bought 2 slaves. And the Irish are very opposed to slavery. So they removed him from the museum in Ireland. All the depictions of him and everything has all been taken down because he owned 2 slaves.
Wow.
And he was pro-slavery because he felt that there was an opportunity to convert people to Christianity. Your slaves. And that horrified me. So now even I kind of with the Irish about that.
Well, they were pretty successful, weren't they, in converting them to Christianity?
They were. Yeah. That's the thought. Yeah. Go on.
Okay,
back to infinity. Back to
so we've gone through Newton and Berkeley, and
but people should know that Newton was a nasty guy.
Newton was a nasty guy. Yes,
Okay.
That's true. And they all should know that he was involved in theology, and he was an anti-Trinitarian. And so it wasn't just that
a
he
rich,
was this
complicated person.
Yes, a rich, complicated person who thought very deeply about these issues.
And I heard this on, I'm sorry, I'm doing tangents because they remember these things from philosophy. Newton, you may dispute this one too, but they said that before he died, he said that he was a virgin and maintaining his virginity was his greatest accomplishment.
Well, that is pretty difficult.
I don't know where to look that up. They just told us that. Maybe that's not true.
Ask Chat AI or whatever.
I'm going to do that.
Yeah, go ask Chat.
Okay. Did Newton die a virgin? And was he proud of it?
Did he die of?
Okay, die of virgin. Well, the idea is, you channel your libido into mathematics.
Well, I could say a lot about that.
Let's not.
Let's keep this, PG.
Yeah, PG. That's right.
So
you're covering the Enlightenment.
We're up to the Enlightenment, and we're going to go beyond that now to the 1800s, because it was only in the 1800s that a really solid foundation for the calculus was developed. And I don't want to get into that entirely. So the solid foundation for the calculus did not involve giving a solid foundation to the notion of the infinitely small. But with Zeno's paradox, what it did say, in a way, essentially, is that if something gets arbitrarily close, then it's there. So a friend of mine was taking a walk while preparing these lectures for church. And she said, she had learned that 0.9999999 is the same as 1. I said, yes, that's true. It is the same as 1. So it seems like a contradiction. Well, why is it the same as 1? Well, you can ask yourself, how much does it differ from 1?
It's non-different from what? It's
non-different. Well, you take the first.
I get it.
First 9, it's different by 1/10. You take the next 2 9s, it's different by 100. You take the next 1,000 9s, it's different by an extremely small amount. And the more 9s you put on there, the less it differs from 1.
Right.
And so, in terms of this, if it gets arbitrarily close, it's the same thing.
It's infinitely close to 1.
It's infinitely close to
I get
1,
it.
and so therefore But they wouldn't say that. They wouldn't say it's infinitely close to 1, except in a very informal sense.
Okay. Arbitrarily.
They would say the sum of the series equals up to 1. And I don't want to get into what that is, but that's the solution to the Zeno paradox.
Wow.
The sum of the series, 1/2 plus 1/4 plus 1/5. So you've got a series, you're adding up all these numbers. And then they have a definition of what it means for the sum of this series to converge and give you this particular value. And that's, I'm going to say, that's the solution to the Zeno paradox. It's not an entirely solution, but it's one that is a pretty good solution. So we're going to put the infinitely small aside for a while. We're going to come back. Yes, I did tell you about smoking hashish, right? And my first encounter with the infinitely large, and my first encounter with the infinitely large came from this book by Felix Hausdorff, which was published in the first edition of it was published, I think, in the late 20s or so. And it was called set theory, Manlehre. And basically what it was the exhibition,
demonstration?
Tell me the word I'm looking
Demonstration.
It was, it was exposition
Oh.
of Cantor's ideas about sets.
Which came earlier.
So Cantor himself lived in the late 1800s, Georg Cantor, and he developed over a period of time this notion of infinity and ordinal numbers and so on. It didn't just come to him as a flash in the night. He woke up one morning and said, "Hey, these are interesting ideas. I'm going to write all these down." And there was a reason why he came to it. And we're going to go back to music for a minute.
Oh.
So music, what we hear when we're speaking, we're hearing a waveform. We're hearing variations in air pressure that produces. So you have a musical instrument that produces very regular variations. And they don't always have to be smooth like that. The clarinet goes something like this. And the idea Bernoulli, one of the Bernoullis, I don't remember which one right now, proposed the idea that you could approximate any waveform by adding up these smooth sinusoidal forms. And that's called a trigonometric series. And the big problem, and the formal study of that in the 1800s, then was Fourier analysis. And the problem was you could come up with, for a given waveform, you could come up with what the trigonometric series for it should be, but you had to determine whether or not that trigonometric series actually converged, if it actually did this business of getting arbitrarily close to where it was supposed to be. And if the functions are continuous, that is, they're sufficiently smooth, there's no problem. But if there are little jerks and fits along the way, then problems start to arise. And Cantor's early work was in trying to show the convergence of these trigonometric series when you had some jerks and fits. He couldn't do it in general, but he could do it if these jerks and fits just occurred. Maybe there were 4 or 5 of them, just some discrete amount of them. And then he thought, well, I've got this discrete amount, but these are going to some limit point over here. And so he started to investigate what kinds of places where you could have difficulty in the convergence of the trigonometric series. And he called these, a collection of these places where you could have difficulty, a set. Originally called it eine Mannigfaltigkeit. What does that mean in English? Never mind, he didn't use that term very long. He changed it to Menge, which means a collection of things, and we translate it as a set. So, so he started studying these sets, and he started looking at the forms that there could be, and these sets, they kept getting bigger, he couldn't describe them. very well just using the terminology that existed, and that's what brought him to the theory of the infinite.
What do you mean the theory of the infinite? I thought they already had that concept of the infinite.
No, they only had up until Cantor, they only had the concept of the potentially infinite.
Got it.
Cantor was the one who introduced and said, hey, this idea of an actual infinite is meaningful mathematically and it's useful.
Does this, well, does this have theological implications?
We'll get to that.
Okay.
We'll get to that. We'll get to it. I talk in church in my Sunday school class, people offer various kinds of talks. So there was a fellow in the class who's an expert on the Shroud of Turin, for example. So he's talking on the Shroud of Turin. We have another guy who sometimes just talks about his hometown. So they talk for them all. And they're looking for speakers, and I said, well, I could give you a talk on the history of infinity or on miracles. And I thought surely they were going to choose miracles, but they chose the history of infinity, much to my astonishment. So I had to, like I say, this wasn't something that I knew nothing about. I knew a lot about it, but I didn't know all of these.
So you learned a lot of this format.
I knew about Bishop Berkeley. I didn't know that Berkeley out in California was named for him. Yeah. I just found that out today.
Yeah.
So, so where was I?
You were on the infinite, the real infinite, not just potential infinite.
That's right, the actual infinite.
And then I asked you if that had theological implications, and it took you that, but now we're coming back.
And we will come back. And Cantor was a very complex person too.
Oh.
So he suffered from periodic fits of depression. He died in the mental asylum.
Like Nietzsche.
I didn't know that.
Well,
he deserved in the mental asylum. So Cantor, he was concerned about the theological implications. And obviously from the name, his family was Jewish, right?
Oh.
But they had converted to Protestantism.
Oh.
And Cantor studied the medieval scholastics. He was interested in scholasticism.
Oh.
And one thing I found out when he was developing this theory of the infinite, he actually went to talk to a theologian to see whether, this was some kind of heretical idea. Was this going to take him away from the path of truth into some kind of heresy? And I think the conclusion was that no, it was okay. But so Cantor was very much concerned. He wasn't like some of the people in modern science who deny God. Everything is just science. It's all mathematics. Right. It has nothing to do with anything spiritual or
that's real postmodern.
Yeah,
like that.
Yeah. So, but in Cantor's time, like everybody in the 1800s, was involved some way or other with some kind of theological idea. So for Cantor, yes, it was significantly involved, and he also claimed at one point that God had appointed him to be the one to bring this theory to mankind.
Okay, probably did. It happened.
It's possible that you, Chris, might say that.
Okay. I did.
Probably a lot of my friends at Clemson would laugh at it.
Okay.
Okay.
They don't believe in providence.
And right. Even the ones who are good Episcopalians might not believe that God actually told Cantor to bring this theory.
Oh, I didn't know you said he told him. I thought he meant for him to. But it was his.
Oh, it was more direct than that.
Literally told him. Yeah,
No,
I'm not very keen on that kind of talk myself, personally. But not that it matters.
If you start discussing that, and then I say he died in a mental institute.
No, that makes sense now. Yeah, God told me. Yeah.
Well, another one of Cantor's problems, as we're going to come back to, everything is numbered. But one of his critics was Kronecker. I don't remember his first name. Doesn't deserve to have it. No, I'm sorry.
By the way, Cantor was in like the mid-1800s.
Yes, he published a series, I think, of 4 papers. He published a number of papers on this, building up to his final ideas.
Well, this was the heyday of Spiritism. Channeling, hearing voices.
Oh.
So it kind of goes with this.
Oh.
God told me to kind of like Blavatsky.
Was that true in England as well?
Absolutely, 100%. Right in the middle of the 19th century.
Oh, you're right.
They were really occult.
Well, I'm familiar with Rudolf Steiner.
Okay, well that's similar.
Because I'm very fond of his educational system, of his approach to education in the Waldorf schools. So that makes a lot of sense.
Yeah,
that's very interesting. So it wasn't like just this one crazy person off to the side who was feeling this.
It was I can't remember the name. It was the inventor of talking to angels.
You're the philosopher.
But I can't remember his name. But I've written about it.
Well, maybe it will come.
It'll come later. Go on. I'm really so we're Look, I just will tell people that the listener that originally this subject wasn't going to be on infinity. I had asked the professor Robert to tell me how all mathematics is reducible to set theory, because I have a professor who was from Harvard who told me that, and I'd actually written that in my own writing, but I only have the testimony. It's just the testimony of Dr. Hill. I've never known how to explain that, or even quite understood set theory.
I have a suggestion.
Yes. Because I believe everything's mathematics. So I want to believe it's all reducible.
I have a suggestion for you. I suggest stop the camera now.
Oh.
That will be the end of this talk.
Oh, we'll do a part 2.
And then we will do a part 2 that begins by addressing your question about how everything is reducible to set theory. How about that, Chris?
That sounds wonderful. And this has probably been about an hour.
It has. I was just looking at
But we do need another hour. We haven't even come to Bertrand Russell and all that.
All I need is to get up and stretch. And
Okay.
So
thank you very much. We'll see you later. This Robert Jameson, and we're in Myrtle Beach. This is October the 15th, 2025, and we'll catch you later. Bye-bye.